Hello everyone, welcome to my channel. In today's video we will learn about Wittig reaction. In Wittig reaction, a carbonyl group is converted to alkene and the reagent that is involved is ylide, YLID. This is PPS3 CH2. Here it will be plus, this one will be minus. This is ylide. Now this also exists as PPS3 double bond CH2. These two are resonance forms. Okay, and this one is called phosphorin. So before knowing what is Wittig reaction, let us first see how this reagent is formed. We will take PPS3, then let us consider methyl iodide. In this what happens, PPS3 belongs to the family of nitrogen, so it has one lone pair, and now this lone pair is given to methyl, and methyl leaves this I as I minus. Okay, this is SN2 mechanism. So the product formed is PPH3 CH3. Here it will be plus, since it is giving its lone pair to methyl, that is why it becomes plus. Now what happens is that there are three hydrogens in this methyl group. These hydrogens are acidic in nature. So in presence of base, one hydrogen gets removed and the product that is formed is PPS3 plus CH2 minus. This is ylide, and this negative charge can get stabilized and can form phosphorin. Now we have taken methyl iodide, but in place of methyl iodide we can also take another organic molecule. For example, we consider this. In this, the ylide that will be formed is PPH3 plus, this one is minus. This ylide will be formed in case of this organic compound. Okay, now we will see what happens in Wittig reaction. In Wittig reaction, generally aldehydes and ketones, these two get converted to alkene. Only the aldehydes and ketones get converted to alkene. We will take some examples. For example, let us consider a simple ketone, acetone. And we provide a ylide. This is phosphorin. Okay, so we will give a ylide. Now see this carbon is electrophilic in nature, right? So what happens, and this carbon is nucleophilic. So what happens, this negative charge, this carbon has extra electron, right? So this carbon gives its electron to this carbon and this pi bond breaks and electrons go up and this oxygen becomes negatively charged, and the product that we get is O minus CH3 CH2 PPH3, here it is plus. Sigma bond forms between this oxygen and this group, and we get a cyclic structure. Now what happens is that scene elimination takes place. In which this bond breaks and this bond breaks, this bond breaks and this bond breaks, and we get the product as CH3 double bond CH3. Here there will be CH2 plus O double bond PPH3. This O double bond PP, it is a very strong bond compared to P double bond C. So the product, in the product we are getting PPH3 double bond O and this alkene, and this one is scene elimination. Why we are calling it a scene elimination? Because this oxygen and this group, they both are on the same side and they are getting eliminated. So this is scene elimination. If the oxygen is in this side and PPH3 is in this side, then this one is known as anti. Okay, this one is cis. So we can say that what happens is this carbonyl group gets replaced by an CH2 group or any alkyl group, and it becomes like this. Now we will see the stereochemistry of Wittig reaction. In alkene formation, we know that there are two isomers that are formed. One is cis, one is trans. Cis can also be written as Z, trans can also be written as E. Now in which condition cis alkene is formed? Cis alkene is formed when the halide is unstabilized. It is formed in case of unstabilized halide. And trans is formed in case of stabilized halide. Okay, now what is stabilized halide? First we will see what is unstabilized halide. Unstabilized halide means, you can see this one. This is unstabilized halide, whereas stabilized halide is something like this. There will be an electron withdrawing group attached. This is stabilized. This is unstabilized. This is stabilized because this negative charge is being stabilized. Here, see, this negative charge is forming pi bond, and this pi bond is breaking, and oxygen is getting negatively charged. So this negatively charged is getting stabilized here. But in this case, this negatively charged is not getting stabilized, so it is unstabilized, and this is stabilized. This is taking part in resonance. Here it can only take part in resonance with this PPH3, but here it is taking part with this ester group as well as PPH3. So it is stabilized. And so we can say that in a stabilized halide, there will be an electron withdrawing group present. Okay, in stabilized halide there will be an electron withdrawing group present. Now we will see some examples. Let us take a halide like this. This is a halide we are taking, and we are taking an unsymmetrical carbonyl compound. For example, we will take something like this. Now what this will form? This is what? This is a unstabilized halide. This negatively charged is not being stabilized, right? It is not taking part in resonance. There is no electron withdrawing group present here. This is an alkyl chain. So this is an unstabilized halide. So the product that will be formed is, here there will be double bond. This carbon and this carbon, there will be forming a double bond. This carbon and this carbon, there will be forming a double bond. And we get this one. Now there will be C2H5 here and CH3 here. Since this is cis, this is a large group, this is a large group, this is a small group, this is small, this is large, this is large, and here there is a hydrogen, this is also small. Since these large groups are on the same side, so it is cis or Z, you can say. But if we take the halide that has electron withdrawing group, this one, this is an electron withdrawing group, right? So this is a stabilized halide, and we provide the same carbonyl group, carbonyl compound. Okay. So what will be the product now? The product now will be a trans. So what happens is, here there will be a double bond, here hydrogen, here there will be a double bond. This carbon will be attacking this carbon. So this will be formed, and now here C2H5 and here CH3. This is a large group. This is a large group. This is now a small group. With respect to this two, this is a small group, right? And there is a hydrogen here. This is also small. Here these two large groups are on the opposite sides, and this, so this is a trans. This is a trans isomer, or you can say E isomer. Okay, now we will see like why cis alkene is formed by unstabilized halide and trans alkene is formed by stabilized halide. For this to know, we will take halide and the carbonyl group, they will be approaching each other perpendicularly. Like is that halide, this is some alkyl group, this is hydrogen, and a carbonyl compound is approaching this halide perpendicularly. So now what happens? This bond breaks now, and this bond breaks. And what is the product now we are getting? We are getting PPS3 plus R H C C O minus H pH. We are getting this one, right? Here this one is a bulky group, and this one is also a bulky group, and the space between them is large, so less repulsion is there. Okay, and also if we see, this is a large group and this is a large group, the space between them is also more, so less repulsion. So this is the ideal approach, we can say. Now what happens is that this bond rotates, because chain elimination will take place now, so this bond has to be rotated. So now what happens, this PPH3 plus and O minus, this pH will go here and this hydrogen here, and now bond will be formed between PPS3 and O, and then scene elimination will take place, and we get the alkene as this. This one is cis, since two large groups are on the same side. This is. Now we will see the trans alkene, how it is formed. We will take the PPH2. Now electron withdrawing group will be attached, because trans alkene will be formed when we are taking a stabilized alkene, and for a stabilized alkene electron withdrawing group must be present. So we will take, here we will take hydrogen, here we will take CO2 ET, and then a carbonyl group will attack hydrogen, here pH. We are taking now a bulky group. Before in cis alkene formation, the unstabilized halide had the bulky group in left side, but now we are taking a bulky group on the right side. The reason will be known after some time. In this, similarly, a bond will be formed, PPH3 plus CO2 ET. Here a carbon is there and O minus, hydrogen, CO2 ET, PPH3, O minus, hydrogen and pH. Now see, if we had taken this CO2 ET on the left side, here if we had taken the CO2 ET, then the structure would have been CO2 ET H PPS3 plus O minus pH and hydrogen. This O minus is electronegative in nature, and this ester has also two oxygens, and so there will be very much repulsion between this group and this oxygen. So this structure is more stable. So CO2 ET will be on the right side, or we can say that the space must be large enough so that the repulsion will not take place. They must be kept apart. They must be kept apart. If we take CO2 ET on the right side like this, then the approach of the carbonyl group will be like this. The pH will be on the top if we take it on the left side. Okay. So this one is formed. Now what happens? This bond will rotate again for the scene elimination to take place, and now this PPH3 plus O minus, here this is CO2 ET, this one is hydrogen, this one is pH. So now a bond will be formed between this PPH3 and O, and again scene elimination will take place, and we get the alkene. This one here, this one is large group, this one is also large group. These two are large groups and they are on the opposite sides, so it is a trans or E alkene. Hope it is clear. If you like my video, please like, share and subscribe.